Hello, Namaskar, welcome to NCERT's live session. This is Simran Singh. You are watching us through PM eVidya. You can also connect with us through our YouTube channel, that is NCERT Official. Before starting our session, let me tell you about some of the basic details. In case you have any queries you feel like reaching to us, then feel free to contact us at our toll-free number, that is 8800440559. As today, we will be discussing in this session about class 12th. So, our official mail ID for class 12th is dth.class12@ciet.nic.in. And for class 12th, the subject that we have for today is chemistry, and our topic of discussion is electrochemistry. And we also have an special expert with us in the studio. Let me introduce her to you. We have with us Mrs. Manisha Sharma. Hello ma'am, welcome. Ma'am is PGT Chemistry and is currently serving at Mater Day School. So, let us learn more from ma'am what we are going to study today.
Sure. Hello everyone. Today I will be taking a very important concept of chemistry, and I am sure you all have seen this chapter in your book. A little complicated chapter, but we will try to ease that. Before I proceed with the chapter, I will just ask you if you have some remote control around you, maybe an AC remote control or a toy car or anything. How does it operate? What happens if suppose I remove the batteries inside it? Have you ever thought of what exactly is around working for you? Probably not. Probably we just think that if the batteries are removed, then the remote is not working, and हम बोल देते हैं कि remote चल नहीं रहा है, खराब हो गया है. So, we are now going to understand the chemistry behind these remotes and the magic of these remotes, which enable us to use the ACs and toy cars and everything that's operational on the batteries. So, before I proceed, just let me take you to the slides, and there are a few objectives that I am going to cover up in this chapter. I am first of all going to tell you or describe you what is an electrochemical cell. I am also going to tell you what is the difference between electrode potential and EMF of a cell. And then we are going to differentiate between galvanic cell and electrolytic cell. Also, we are going to understand about standard hydrogen electrode, its importance, its functioning, the dependency of electrolyte and temperature, the Nernst Equation, and the relationship between standard potential, Gibbs energy and its equilibrium constant. Let me first take you to the types of cell that we have. See, there are on the slide, if you can see, two types of cell. One is called galvanic cell and another is called electrolytic cell. The galvanic cell and electrolytic cell has a very major difference, if you would see, or probably you would say that ma'am, both the cells look same. So, if you look at the diagram, one of the galvanic cell has a bulb connected to it, while the electrolytic cell has an external source connected to it. What does that mean? Electrolytic cell works on the source. That means this particular cell will only work when it has a connection of electricity. What happens if the light goes off? What happens to the mixer grinder? What happens to the oven? What happens to all these instruments? They stop working. But the batteries and all, they work on the spontaneous action of the reactions taking place. And where are these reactions taking place? The reactions are taking place within those batteries which you have put in these remote controls and all these devices which operate on batteries. I hope that gives you a clarity between the galvanic cell and the electrolytic cell. Next, I will just take you back to your class 11th. Would you like to go back to class 11th? Probably no, because we are not serious in class 11, and with pandemic time, we had a lot of fun in the online classes, right? So, let me revise and review the redox reaction that we did. What is a redox reactions? I am sure all of you would agree that redox stands for red and ox. So, we have reduction and oxidation reactions happening simultaneously. How do we justify this reduction and oxidation reaction? Of course, with the transfer of electrons. When we talk of this transfer of electrons, let me take you back to a very common reaction which all of you are familiar with, and you have zinc and copper ions working together. The zinc is reacting with copper ions and giving you copper and zinc ions. What is happening in the reaction? If you can see, though I have marked it on the slide, but I would still like you to brainstorm and tell me what exactly is happening. In the zinc container, or probably with the zinc metal which is in solid form, it is ionizing, losing 2 electrons and converting itself to zinc 2+. Copper 2+ on the other hand is gaining those 2 electrons and giving you copper. Whoever loses the electron is undergoing oxidation, and whoever gains the electron undergoes reduction. I will be giving you a trick to remember that also, so stay tuned. Then we have zinc undergoing reaction to zinc 2+ plus 2 electrons. Since now we have divided the equation, it is known as a half reaction. So zinc giving me zinc 2+ plus 2 electron is reduction oxidation half reaction, and copper 2+ plus 2 electron giving me copper is reduction half reaction. And so in other words, you may also say that zinc undergoes oxidation as it loses 2 electrons, while copper undergoes reduction as it gains 2 electrons. The 3 pointers that I have mentioned on the slide are all the same things, but we are saying it differently. The top part I have shown you the reaction and marked the loss and gain. In the second part, I have divided the reaction, overall reaction, into 2 halves, and so I got the 2 half reactions. And in the last part, I have just defined the definition or the explanation for oxidation and reduction reaction. As I said, I am going to give you a trick, because I give a lot of tricks for you to remember. Do not cram chemistry, please, never and ever cram chemistry. Just understand it, and I am sure you will fall in love with the subject. So we have a trick for this, and the trick is oil in rig, right? So Dubai and all these countries, they have, a lot of rigs there. Why? Because they are very popular for the oil content there. So what is this oil standing here for? O stands for oxidation, I stands for involves, and L stands for loss. Similarly, for rig we have reduction, involves, gain. There is another trick that I have which is not mentioned in the slide, and that's called Leo does Ger. So all of you with the Leo zodiac sign there, this trick might be very familiar with you. Leo, the L-E-O. What kind of sound does a lion make? Lion roars. And how does it roar? Probably you must be feeling कि मैम क्या कर रही है ना, sound सिखा रही हैं बच्चों की तरह. But it helps. So Leo, the lion, is roaring, and what kind of sound it is going to make? It's going to do grrr. So we have Leo does Ger, where Leo stands for loss of electron, which is oxidation, and gain of electron is reduction. So this is another trick. Whichever trick you like, you may relate to it, and I am sure you will never and ever get confused with the concept of redox reaction. Let's go ahead with the next content, which is known as electrode potential. This is something very important for you to understand. Let us see it with a diagram. In the diagram, you can clearly see that I have a zinc sulfate solution, and I have put a zinc rod in it, right? So that grey part that you see is the zinc rod, which is dipped in zinc sulfate solution. Now what is going to happen? As soon as you put zinc rod and dip it into zinc sulfate solution, the zinc is going to undergo oxidation. As soon as it undergoes oxidation, it is going to lose the electrons. How many electrons is it going to lose? 2 electrons, because Zn2+ is a stable state for zinc. So if zinc has to lose the electron, it is going to give you Zn2+. Achha, before that, before I proceed, let me also tell you, why would zinc convert itself to zinc 2+? Why not zinc plus? Why not zinc 3+? It's because every one of us wants stability in life, right? And what is the configuration for zinc? The configuration for zinc is, think. The configuration of zinc is 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2, right. So we have, again we then have 3d10, right. So we have 2 electrons in the outermost shell. So if you have to remove the electrons and convert it into a cation, you have to remove the outermost electron, and you can only remove these 2 electrons because if you go inside the shells, you are disturbing the stable configuration, which of course we cannot afford. So even poor zinc cannot afford that, and zinc is going to say no, 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 I am only going to lose 2 electrons, not more than that, right. So zinc is going to lose 2 electrons and will convert itself to zinc 2 plus. This is going to definitely create some barrier, right. If your mother comes to you and tells you that you have a cousin visiting your home and you have to give her a pair of jeans, कैसा feel करेंगे? कितना बुरा लगेगा ना?
I won't give it.
My God, she won't give it, and probably many of you won't give it, huh? So if you have to take electrons for someone, it is important that there is going to be a difference between that person and you, and you are going to probably crib, पता नहीं क्यों आ गया, मेरी jeans लेने के लिए आ गया, right? So similarly, the same thing is happening in our electrode potential system also. When zinc is losing these 2 electrons, it is developing this potential difference, which you can see on the slide, and you can see these plus plus signs there, right. So there is this potential difference which is created. Why is this potential difference created? Because the positive and negative charges have separated, right. So zinc has converted itself to zinc 2 plus ions, and so this separation has created a potential difference, and this potential difference between the metal electrode, which is the zinc, and the ions, that is zinc 2 plus and sulfate 2 negative, the potential difference between these ions is basically called electrode potential. Now on what factors does this electrode potential depends on? The electrode potential depends on a lot of factors, but these 3 factors are the major important ones. What is your metal electrode? What are the ions that are given by the electrolyte? What is the concentration of the ions, and at what temperature are you studying this electrode potential thing? So keeping that in mind, we have to understand and see what electrode potential is. Now, whenever the electrode potential is measured under standard temperature and conditions, probably as a science student you have heard this term standard temperature and pressure a lot of times, and in short we call it STP. So under standard conditions, the electrode potential is known as standard electrode potential. For this, the temperature should be 298 Kelvin and the concentration should be 1 molar solution. The pressure of course has to be 1 atm, and if all these 3 conditions are followed, we get E naught, which is a denotion or which is a symbol for standard electrode potential. Now as per the IUPAC convention, earlier we used to call standard reduction potentials. So probably if you have some elder brother or sister at your place, or you have some elder sibling who has studied science some time back, probably his or her books would say standard reduction potentials. But now the nomenclature for standard reduction potential has been changed, and so we now call it standard electrode potential. Gone are the days when we used to call it standard reduction potential. We don't call it anymore. So we now call it standard electrode potential. So that's a change. Okay. Once I have this, then now I'm going to show you something happening on the slide. So everybody's eyes on the screen, and so you will have to really appreciate this. This is a setup, and I am going to show you how exactly the reaction happens, right. Right now we were just discussing one container with zinc sulfate solution and zinc rod in it. Now I have 2 containers. One container has zinc ions, the another container has copper 2 plus ions. See what happens? Oh, what happened? One electron went from this portion to another portion. The other one is also following. So we basically have these electrons moving. I will show it once again to you. So the electrons are going from one container to another, and the another is going this side. Now electrons, they move from left to right, and current moves from right to left. This is something very, very important for you to know, because as a science student you must be studying physics, you must be studying electrostatics there, and in electrostatics your teacher must have told you the direction of current. Chemistry is opposite to the concept of physics. गलत कोई नहीं है, फिजिक्स भी सही है और केमिस्ट्री भी सही है. It's just that one is saying that the half glass is filled and the other one is saying that the half glass is empty. So every time we explain this concept, I have my students saying, no ma'am, in physics we studied that current moves from right to left. So I am just making and giving you a clarity that current would go in reverse direction to the flow of electrons. So if the electrons are flowing from left to right, the current will flow in reverse direction. Now what happens? What happens? Zinc has given its 2 electrons. The electrons went from the left container to right container. What if? Now, what now? We do not have anything. The process has just stopped. Why did it stop? Because there is a lot of accumulation of charge and electrons on the right container. Can you see it on the slide? And so we see that nothing is happening. It's kind of a diversion or kind of a jam there. आप एक गलत सड़क पे चले गए, आगे तो सारा ब्लॉक था, आपकी गाड़ी फंस गई. आप क्या करेंगे? So we will have to look out for some option, we will have to look out for some way जहाँ से अब हम निकल सकें. And so right now my circuit is incomplete. If you see, my circuit is incomplete. Zinc is losing, copper is gaining and nothing is happening. Electrons are right there, nothing is happening. And sulfate is also there because copper sulfate and zinc sulfate solution. So for this purpose comes to the rescue and we have a salt bridge here. This salt bridge solves our problem and this salt bridge completes the circuit, and so every time electrons are moving. See, this is another diagram, a little complicated one, but probably it will give you a better clarity. So you have a left hand side container with zinc solution, right hand side container with copper solution. Zinc is losing the electrons and giving you Zn2 plus. Copper is gaining those 2 electrons, becoming copper 2 plus, and ultimately the salt bridge is enabling these electrons to migrate from one side to the another. And how are we monitoring that? We are monitoring it through the voltmeter, the key, and you can very clearly see how the electron is moving from the left container to the right container. So a salt bridge comes as a savior here and it flows from left direction to the right direction. Are the things so far clear? Any queries, any questions? Okay, we'll go ahead. And so we have a major description or an understanding about the galvanic cell. The galvanic cell is, this picture is a little, simpler version of this picture that I am showing you on the slide. So this one is a simple one with not many markings and labelings. So you still have the same thing. You have a zinc rod dipped in zinc sulfate solution. You have a copper rod dipped in copper sulfate solution. Voltmeter to measure the voltage. Salt bridge between the 2 containers to complete the circuit. And so we have a galvanic cell here. Now whenever we have this kind of system, you have the potential difference. I told you what is potential difference. Every time the system is losing the electrons, the solution is losing the electron, or rather I would say electrolyte is losing the electrons, it is converting itself to some ions, some charged species. These charged species have their own potentials, and the difference between these potentials, between the 2 electrodes at standard condition, that is 298 Kelvin, 1 atm pressure and 1 molar concentration, is now called EMF, which is electromotive force, and so we denote it as E0 cell. What is the standard electrode potential? E0. What was that? It was for a particular electrode. I'll just clarify that to you. Standard electrode potential we are showing through E0. E0 is only when the electrode potential or the potential difference is measured between 2 electrodes under standard conditions. And so we have now electromotive force, and if we have to now calculate it, it is given by E0 right minus E0 left. So I will have to calculate the E0 of the copper solution, and also I have to to calculate the E naught of the zinc electrode, the difference of these two will give me E naught right minus E naught left, that is E naught cell. Or I can also say that E naught cathode minus E naught anode, because the right hand side container is called cathode and the left hand side container is called anode. I will give you a trick to remember this also, the containers, why are we calling them anode, what is happening at anode, what is happening at cathode, I will give you a trick for that also. But so far this is the galvanic cell and this is how we calculate the E naught cell. Probably this table is very familiar to all of you and you all have seen it in your textbooks, and this is a very simple picture where you are talking about the reduction half reactions. So I told you that we no longer call it reduction potentials, we call it electrode potentials only. So whenever we are doing E naught cathode minus E naught anode, we have to figure out what is the electrode on the left hand side, what is the electrode on the right hand side, and accordingly we are taking the values and we are simply subtracting it. I have done the calculations for you to know how can you calculate EMF. So E naught cell is going to be equal to E naught right minus E naught left, or we can say E naught cathode minus E naught anode. I have taken the values from the table, I have marked it for you as well on the table. So you can see copper 2 plus to copper is 0.34 and zinc 2 plus to zinc is 0.76 negative. So when we put it or when we substitute it in the formula, we get 1.1 volt. Probably now you can check the batteries of your remote controls and all, and I am sure the batteries are labeled with the voltage 1.1 volt. I am sure you have seen that, right? So we have a few queries given by all of you, and it says what is the difference between electrochemistry and classical chemistry. See, classical chemistry is a major or a very broad term, because even quantum chemistry is considered in classical chemistry. The Bohr's theory that you have studied, the Schrodinger's theory, the spectrum and all of these things, everything comes under classical chemistry. Electrochemistry is a specific branch where you are talking about electrical transformations, where you are talking about the conversion of chemical energy to electrical energy or vice versa maybe, and the study of all of that is known as electrochemistry. So that's the difference between electrochemistry and classical chemistry. So it is a branch of chemistry only, but it is majorly dealing with the electrical transformations. How cells are designed? The cells are designed on the basis of what is the usability of the cell. Like for example, suppose I have to design a cell with a low voltage. Probably I will go for a primary cell, like the ones you get in the market, the ones you are using in your remote controls and toy cars and all. They are not rechargeable, they are single use cells. So once the chemical inside it is gone, used, you can't recharge it. On the other hand, you have your laptop batteries, you have your cell phone batteries. What happened to those batteries? Imagine आज आपके फ़ोन की बैटरी डैमेज हो गई and you are telling कि मेरा फ़ोन तो ख़राब हो गया, बैटरी ख़राब हो गई है, न्यू फ़ोन ला दो. Is it possible? No. Why? Because the batteries in the mobile phones and laptops are rechargeable. You can charge them, right? So it depends on what kind of usage you have, and of course the electrolyte and the composition of the battery is going to be decided accordingly, right? So we have got cells like Leclanche cell as the primary cell, and it is not chargeable. You cannot recharge it. Once used, you have to discard it. But we have lead storage batteries, the inverter batteries. They are made up of lead sulfate, so that is why they are also called lead storage batteries. So they have got this lead sulfate solution which undergoes reaction, and every time you are charging it, the reaction is reversed. Every time it's discharging, the reaction is happening. Every time it's charging, the reaction gets reversed. So of course it has certain lifetime or some lifespan under which the reaction takes place. So that's how the cells are designed. Electronic configuration, how to do this easily. Okay, electronic configuration, because this is a question, I will just share this thing with you. Probably, I'm sure you are aware about the Aufbau principle. So, when you have Aufbau principle, we simply have n is equal to 1, n is equal to 2 and n is equal to 3. I'll probably write it on the screen and maybe I can show you from there. So, we have number of shells and these number of shells can be
Actually, the question is
mentioned.
not specified, I think.
Yeah. Because they are just saying electronic configuration, how to
Like
do this
one
easily.
is 2, 2p6.
Actually, that's a rule. But you know, if now you can see, probably I'll ease the process now. You can see the screen, right?
Yeah, it's quite visible now.
Okay. So, we have Aufbau principle. For this, I am taking you back to the 11th concept. This is from 11th. So, you have n is equal to 1, which is your number of shell, then you have n is equal to 2, then you have n is equal to 3, then you have n is equal to 4, right? Accordingly, we have the azimuthal quantum number, which is L, right? So, when we have n is equal to 1, L is 0, when it is n is equal to 2, it is 1 and 2, if it is 3, it's 1, 2, sorry, 0, 1, 2, 0, 1, sorry, something like this, and for 4 we have 0, 1, 2, 3. So, for 0 it is S, for 1 it is P, for 2 it is D, for 3 it is F. So, if I have to now make a combinations of it, it is giving me 1S, then I have 2S and 2P, when I have 3, I have 3 0, then 3 1, then 3 2. So, 3S, 3P, 3D, then I have 4S, 4P, 4D, 4F. Similarly, I will have 5S, 5P, 5D, 5F, 5G and so on and so forth. So, for the Aufbau principle, you have to cut it like this: 1, then 2, then 3, then 4, then 5, then 6, then 7, then 8. So, you are making some paths here. Let us connect the dots and that gives you a way. That is giving you a way कि आपको कैसे move करना है. See, the dotted one I have shown you, something like this. So, since you asked how to remember it, if you know how to draw this, then probably you know that the electrons will be first filled in 1s, then they will be filled in 2s, then they will be filled in 2p, then they will be filled in 3s, then they will be filled in 3p. So, if I will just simply take an example of fluorine, which is 9 electrons, the atomic number is 9, I will have 1s2, 2s2, 2p6 and then you have 1s, 2s2, ये तो 10 हो गए, तो ये तो गड़बड़ हो गई, तो अब हम इसको क्या कर सकते हैं, इसको 5 कर सकते हैं. So, ये क्या हो गया, accumulation हो गया 2, 2, 4 and 5, 9. So, 9 electrons have been accumulated. So, I hope this gives you a trick and this gives you explanation that how electronic configuration can be done or remembered easily. This is just a way to do it, and Aufbau's principle is something that we teach in class 11th. So, this is what I have revised for you. Then you have what is interpair effect. I think the child wants to know what is inert pair effect.
Basically, the question that has been is period 5 increase plus 2 oxidation state. So, in that context, somebody has asked what is interpair effect.
Actually, it should be inert pair effect. What happens when you are filling these electrons? Like Abhi, I'll take you back to my sheet. And I just told you that I have 1s electrons being filled in 1s, then you have electrons filled in 2s and 2p. So, if I have to show you the nucleus, suppose this is my nucleus, I have 1s, I have 2s, I have 2p, then I have 3s and so on and so forth. So, what is happening, the outermost shells are trying to protect, these electrons are very, very vulnerable. Anybody can come and take off these electrons. वो कहेंगे न्यूक्लियस तुमको प्यार नहीं करता है, न्यूक्लियस इज नॉट गिविंग यू फोर्स ऑफ इनफ अट्रैक्शन and as a result these electrons are not there. Abhi aap log, you people are 16-17-year-old, right? So when you are 16-17-year-olds, at times you feel na hum ab bade ho gaye hain, why are our parents not leaving us, why are they wanting us to hold our hands and take us everywhere, hum bade ho gaye hain, ab hum akele apna sara kaam kar sakte hain. This is the first thing that comes to every teenager mind, right? So these electrons are also trying to fly out. They are saying hum to jana chahte hain, hum bahar jana chahte hain, we want to be free birds, but the inner electrons are saying no 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 no. छोटे भाई बहन होते हैं ना, कहते हैं नहीं नहीं दीदी नहीं जाना, मम्मा गुस्सा करेगी, मम्मा से बिना पूछे नहीं जाना. So the inner electrons who are trying to protect these outermost electrons are basically giving you the inert pair effect. वो कह रहे हैं नहीं जाना, मम्मा पापा से पूछे बिना नहीं जाना. And these दीदी भैयाज are saying no no, हम बहुत बड़े हो गए हैं, 1-2 साल के बाद हम एकदम अडल्ट हो जाएंगे, we will have the right to vote, we will have all the rights and everything, let us go, हमें जाने दो. एंड ये छोटे भाई बहन बोल रहे नहीं 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 जाना, एंड दे आर ट्राइंग टू प्रोटेक्ट यू, राइट, बिकॉज दे नो आप बाहर जाओगे तो प्रॉब्लम हो सकती है. सो दैट इज व्हाट इज नोन एज इनर्ट पेयर इफेक्ट. आई होप द
very nicely ma'am has answered all those questions. Thank you ma'am. We may move to our next slide.
Yeah, thank you. So we have the calculation part. I have told you the calculation for 1.1 volt, how I am getting this 1.1 volt from this table. And so what happens if I am now increasing this 1.1 volt thing? What would happen if I have the external voltage, the external potential less than 1.1, greater than 1.1 or equal to 1.1? If it is less than 1.1, the electrons flow from zinc to copper, that means from left to right, and current flows from right to left. Very simple. When it is equal, the external voltage is equal to 1.1. Now what is this 1.1? This 1.1 is the battery capacity. तो बैटरी कैपेसिटी से ज़्यादा अगर हम यूज़ करेंगे तो क्या होगा, कम यूज़ करेंगे तो क्या होगा, एकदम बराबर यूज़ करेंगे तो क्या होगा. सो इफ़ यू आर यूजिंग इट टिल द बैटरीज potential, no problem. The cell will work, the battery will work, your device will work, the AC remote is working, the toy car is working, everything is going fine. When it is about to reach equal to 1.1, then probably nothing would happen, right? Why? Because the reaction or the system is now in equilibrium. So neither the electrons are flowing nor the current is there. So nothing is happening, no chemical change is occurring. But if it is greater than 1.1, what happens? It is reversing the process. So if you are exhausting the potential of the battery, what is going to happen? The current is going to move in the reverse direction. So you can very clearly see that electrons will now flow from copper to zinc and current will now flow from zinc to copper. So the first and the last diagram is completely reversed here, and that's the beauty of the calculation, right? So how do we represent this galvanic cell? We have the left electrode, zinc undergoing oxidation to zinc 2+. We have the right electrode, copper 2+, undergoing reduction to copper. 1 molar solution is on the both the sides. So how are we going to represent it? We will simply write the left electron, we will simply write the right electrode, and we are going to separate it with 2 vertical lines. The 2 vertical lines that you see between zinc 2+ and copper 2+ is for the salt bridge, or is actually showing you that you are separating the 2 containers, or probably you are talking about 2 electrode system. Now as I said, I am going to give you another trick to remember what is happening in the left container and right container. So the trick is lone. Lone, which is a very common word and we all are familiar with. So in this word lone, the L stands for left, that means left container is going to experience oxidation. The electrode is going to be called anode, and it is going to have a charge of negative charge. So the opposite is happening on the right hand side. What is the opposite on the right hand side? L ka opposite is right. So the right container will experience reduction. It will be called cathode, and the charge on it will be positive. So you just remember lone, and the opposite can be done on the right hand side. So I think that gives you enough understanding about the containers and all. Now because you people asked one doubt, what is the difference between electrochemistry and classical chemistry, we also have a doubt, or we also have a difference between galvanic cell and electrolytic cell. Now galvanic cell is going to occur, or is going to experience the reaction which are spontaneous, अपने आप हो रही हैं वो reactions. Electrolytic cell will have an external voltage source, तो आपको plug in करना पड़ेगा, current उसको देना पड़ेगा, तभी वो cell work करेगा. So these are 2 differences, major differences between galvanic and electrolytic cell. Apart from that, galvanic cell converts the chemical energy into electrical energy. So the reaction is happening, is giving you potential, is giving you all the flow of electrons and transfer of electrons, and that's how you are getting the electrical energy. In the electrolytic cell, you have the electricity which is being plugged to the device or the cell, and that is giving you the chemical energy, and ultimately the reaction is happening, right. So, these are two major differences between the galvanic cell and electrolytic cell. Cathode is positive in galvanic, anode is negative. In electrolytic it is opposite, anode is positive and cathode is negative. So, these are again some of the differences, and this is a galvanic cell which is also called voltaic cell. It is also called Daniell cell. So, it is just various names that we give to these cells, and this is what is happening. So, you can very clearly see in the galvanic cell I have not plugged in, कोई charge नहीं लगाया है, कोई current नहीं plug in कर रखा है, कुछ नहीं है. The reactions are happening in the containers. Ultimately, they are undergoing certain chemical reactions. That chemical reaction is giving you chemical energy, which is being converted to electrical energy, and so the battery is working. Now, we come to something very important, which is called standard hydrogen electrode. Till now, I have discussed what happens if you have single electrode. I have also discussed what happens when I have one electrode connected to another electrode. What if I have one unknown electrode and I have nothing to connect with it? What happens? I have the salt bridge, but salt bridge is going to go between the two electrode containers, and I don't have the second one. So, what am I going to do? In that case, I need something whose value I am sure of, whose value is known to me, and that electrode can be standard hydrogen electrode, which you can see on the screen. So, this electrode is a very special electrode, looks very simple but is very special. You have this inverted U-tube kind of tube, in which we have finely divided platinum coated platinum foil. We are giving the hydrogen gas at 1 bar, and there is this 1 molar hydrogen solution. Hydrogen ions are present in the container. So, every time this hydrogen gas is pumped in, it is releasing a lot of bubbles, that is the hydrogen gas, and ultimately the standard hydrogen electrode is being used. Why are we needing this hydrogen electrode, and why are we using this platinum only, why not anything else? So, the reason and options are given on your screen. Platinum, first of all, is chemically inert. It is not going to react, it is not going to undergo any kind of reaction with any acid bases or anything. It is a very good conductor of electricity, and we are of course talking about something which is based on electricity. The platinum foil, the little small platinum foil that you see there, which is marked with the arrow, is coated with platinum black. This increases the surface area of the platinum foil, and so more and more hydrogen gas can be absorbed. We are also giving a stream of hydrogen gas from the top, see, and this hydrogen gas is saturated, and we also are maintaining a 1 molar HCl solution, and that is why you can see 1 molar H plus ions which are given by this HCl solution. To maintain and to refer it to as standard hydrogen electrode, the standard condition of 298 Kelvin and 1 bar pressure is required. So, this is the process, or this is the importance of the standard hydrogen electrode. Now, what happens in this standard hydrogen electron? The oxidation is happening, and you see that hydrogen gas molecules are converting itself to H plus ions. So, loss of electrons, so oxidation is happening. Now, at the cathode, of course, reduction has to happen. All the H plus ions that are being lost as a product of oxidation are going into the solution, and ultimately a redox reaction is being done. This kind of mechanism or chemistry is studied in standard hydrogen electrode, and we represent it as PT, which stands for platinum, hydrogen gas with H plus ions and 1 molar solution. So, you can very clearly see I have written PT comma H2. Why comma? Because we are using the metal here. Metal is not participating in the reaction. So, we are not going to show it with the slash. We are going to show it with the comma, which means that hydrogen gas is interacting along with platinum and getting itself converted to H plus ions. The value of standard hydrogen electron is arbitrarily taken as 0. So, every time you are connecting it through something, see, I have shown it to you. Every time, suppose you have a copper sulfate solution in a copper container, You do not have the second container. What are you going to do? You will simply take this standard hydrogen electrode, combine it with the copper electrode. As soon as you combine it, you know the potential of hydrogen electrode is 0. Whatever value the voltmeter is telling you is now basically the value for copper electrode, because E cell is equal to ER minus EL. ER is 0.34, copper from the table we know, EL is standard hydrogen electrode 0. So ultimately whatever is given by voltmeter is the electrode potential. Similarly for the zinc, if you are going to do that, in the zinc you have to put it on the right hand side, that hydrogen electrode, and ultimately again you are applying the same formula, ER minus EL. The zinc value is minus 0.06, so you simply calculate and you get the value. And with this we come to the important concept like Nernst equation. I have already represented the cell in front of you. This is something very mathematical. So all of you out there without maths, because I know some of you must be medical students or aspiring doctors out there. So probably you might not have maths. So a little amount of maths is involved in chemistry, and so I'll ease that with every single step. I will show you each and every step on the slide. So please be attentive while I tell you this explanation. So I have given you this cell representation where zinc is undergoing oxidation to zinc 2 plus and copper 2 plus is undergoing reduction with copper salt. Now we have the elaboration of this reaction. So again, towards the end or towards the bottom, you can see that zinc is undergoing conversion to zinc 2 plus plus 2 electron and copper 2 plus plus 2 electrons to copper. When we add, we get the overall reaction. Now the Nernst equation says that the electrode potential or the electrode value of the container should be equal to its standard electrode potential minus RT upon NF log of the metal and its ions. So for that, if you see, if I am talking about copper, I have written E copper 2 plus to copper gives me E naught copper 2 plus to copper minus R here stands for gas constant, T here stands for temperature, N here stands for number of electrons and F here stands for Faraday's constant. Then we have Ln, which is natural log. In science, in chemistry, we do not simply apply log. We have to apply the natural log, and natural log is represented as ln. Though we cannot solve natural log, so ultimately we have to convert it to base 10 or what you call as log log. So whenever you are combining or whenever you are converting it to log, you have to introduce a factor of 2.303. Please mind it, when you do it directly in maths, you do it and use it as log. But if you are doing it in science, you first take natural log, ln, and that ln, since it cannot be solved, has to be converted to log. And log convert karne mein you have to put this number as 2.303. That's the difference between natural log and log. So in the lower slide you can see lower line you can see 2.303 RT upon NF log Cu upon Cu2 plus. Now the concentration of metal was 1, so we are taking it as 1. Copper 2 plus, we have put it in the square bracket. Similarly, you can calculate it for the right hand side container also, left hand side container also, that is E Zn2 plus Zn, which gives you E naught minus 2.303 RT upon NF log metal upon metal ions. Again, the concentration of pure metal is taken to be 1, so we have replaced it with the 1. We combine the two reactions, we do right and left. So the right container is my copper container, the left container is my zinc container, and so I simply do E cell is equal to E right minus E left. And when I substitute all this that I have found out here, I get the expression as E cell is equal to E naught cell minus 2.303 RT upon NF log zinc 2 plus to copper 2 plus. You can do it yourself also, it is very simple. You just have to simply take the last line of the copper ions, last line of the zinc ions, simply place it in right and left thing, subtract it, and you will get this expression. Here I have elaborated that E cell is the electrode potential under given condition, E naught cell is the electrode potential under standard condition. R is the gas constant. We take 8.314 joule per Kelvin per mole. We do not take 0.0821 liter atmosphere per Kelvin per mole here. We are taking the other value of R. Temperature has to be 298 Kelvin. N is the number of electron lost or gained, and F is 96500. Just to simplify it for you, because I know R value is 8.314, temperature is standard 298 Kelvin, and Faraday we take as 96500, though exactly it is 96487, but just to ease your calculation we take it 96500. When you substitute R, T and F, you get this factor called 0.059. So if you are seeing the above expression and the lower expression, probably you are confusing yourself that ma'am ye achanak se kya ho gaya. So I am just clarifying that doubt, that I have now just substituted 2.303 into 8.314 into 298 divided by 96500. If you have your calculators around you, you can quickly calculate and you put the values there, and obviously you will get 0.059 upon N, and rest of the thing remains the same. Similarly, because we have been talking about zinc and copper for so long, let me take another example of magnesium and silver.
Before we proceed to another example, let me inform all our viewers out there that we are left by the last 10 minutes. In case if you have any doubts, reach out to us through the comment box of NCERT official. Yes ma'am, you may proceed with that.
Thank you. So we have this example of magnesium and silver, and in this you can very clearly see that magnesium is undergoing oxidation, and when it undergoes oxidation you can see it's converting itself to magnesium 2+, and we have silver converting itself to silver. So silver ions converting itself to silver. So when you combine the two, you are equating it as magnesium plus 2Ag, Mg2 plus 2Ag, and ultimately the EMF again can be calculated. I'll give you a trick to do that as well, and the trick is that every time you are doing EMF is equal to E cell, it is E naught cell minus 0.059 upon N. ये तो fix है, ये तो आपको पता ही है. Log Mg2 plus or Ag plus होगा या Ag plus or Mg2 plus होगा. So for that we have this thing as log L upon R, again another trick. So just like we have E naught R minus E naught L, similarly when you are substituting it here, you can do it log L upon R. So whatever is your left hand side ion, it will come in the numerator, and the right hand side one will come in the denominator. Why have I squared the Ag positive concentration? Because Ag positive has 2 as the coefficient, so that will go in the power. Magnesium 2 plus doesn't have any coefficient, so it remains as it is. And when you substitute all these values, you get the value as 3.17, and ultimately that's the value. Similarly, we have a relationship with Gibbs free energy and equilibrium constant. So every time we have this anode and cathode thing, or I said L upon R, if you have E cell as 0, it will be the equilibrium point. Class 11th you have already done equilibrium. So the system is in equilibrium, and as soon as we substitute E cell is equal to 0, we get E naught cell is equal to 2.303 RT upon NF. Now this anode and cathode, there will be no change, no, in equilibrium there is nothing happening, no chemical reaction happening. So this entire factor of anode upon cathode gets converted to the equilibrium constant. So that's how you get E naught cell, and Gibbs free energy can also be calculated as minus NF E naught cell. These are two things that you have already studied in class 11th in equilibrium. So it's just a connection, or connectivity with what you studied in class 11th to what you are studying in class 12th. So just a summary of the Nernst equation. So if you have to write the Nernst equation, it is going to be E naught cell minus 2.303 RT upon NF log anode upon cathode, or 0.059. You can just substitute all the values and you will get the factor of 0.059. At equilibrium constant, E naught cell is going to be 2.303 RT upon NF log Kc, and Gibbs free energy is going to be minus 2.303 RT log Kc. Just a quick recap of whatever we have done all this while. So electrochemistry, probably this will answer again that question, what is the difference between electrochemistry and classical chemistry. So electrochemistry is based on redox reactions. So what you studied in class 11th is being used up here now. This redox reaction has two components, oxidation and reduction. This redox reaction is basically generating the chemical energy because the reaction is happening. The chemical energy is now converted by the galvanic cells into the electrical energy, and ultimately this electrical energy is getting converted by electrolytic cell back to redox reaction. So basically that's the roadmap of the redox reaction, and that's what is being studied in electrochemistry. Apart from that, the galvanic cells have two components, anode and cathode. The anode is the left part undergoing oxidation, will be called anode and will have negative charge. So lone you can remember, and for cathode you will have right, reduction, cathode and positive. We also remember it with another trick which called an ox, red cat. So ox is an animal, cat is an animal. So we say an ox, red cat. So an means anode, ox means oxidation, red means reduction, cat means cathode. So anox, red cat. And the electrode potential is calculated with E naught cell is equal to E naught R minus E naught L. The flow of electron will always be from anode to cathode, and flow of ions will always be from cathode to anode, and the whole circuit needs to be completed if you want the reaction to happen. This is another thing, standard hydrogen electrode, whatever I have spoken, the construction of it, how does it work and what is the significance. I am sure that is going to give you a very good recapitulation, and for your exam time also the standard hydrogen electrode will be something that you may remember. As an assignment, if you are very interested and if you have understood whatever I have explained to you, I have a small assignment. You can do it at your end and probably you can share the solutions with us. And so you have a cell that I have shown you. There is iron which is converting to Fe2 plus, you have standard hydrogen electrode on the other side, and you are asked to calculate the EMF. You can also calculate the delta G naught and Kc for the galvanic cell, where E naught cell is already given to you. So keeping all these points in mind, you can do this question. And we have one or two questions with us. One is called what is screening effect. I told you, I will show my sheet again to you. You have a nucleus and you have certain shells here. Now all these shells have some kind of nuclear force of attraction with these shells, right? So the tendency of the outermost electron is to go away. The electron here wants to go out, right? And everybody wants to go out. So the protection, the effect to protect or to screen these electrons is called screening effect. So screening effect is the tendency of the atom that it is saying, don't take my electrons, please do not take my electrons, I cannot afford to take my electrons. So please don't take my electrons, and in that order it is trying to protect. So you might see that the shells are shrinking inside, and that's why probably when we talk of atomic radius across the period, sorry, we say that the atomic radius decreases across the period. Why is it decreasing? Because of the screening effect, and because to reduce the gap, or to maintain the internuclear force of attraction with the outermost electron to the nucleus. So that's what is known as screening effect. Another thing that is being asked is what is the effect of catalyst on Gibbs energy. See, catalysts are those substances which never participates in the reaction. They are not part of the reaction, they just assist the process, they just help. Like what is this eVidya program doing with you? We are trying to assist you. We are trying to get over that barrier of you people missing out your school classes, missing out on those real classes, and so we are doing these virtual classes, these workshops, these sessions with you, so that you are in touch with the content, right? So catalyst is also doing this. They are not being paid, they are not being asked for anything. The poor babies, they get into the system, they do their work, they do the reaction, they do all the things, and then they quietly come out of the reaction and they say hamara kaam ho gaya, bas ab khatam ho gaya. So catalyst of course have a very good impact on Gibbs energy, and if you have a catalyst in any reaction, then definitely the reaction is going to be activated. and it's going to proceed at a very, very good speed. So,
yeah, thank you so much, ma'am, for explaining about these questions. And we were having another questions also, but we'll try to take that in the next session. Once again, I would like to thank everybody who has participated in this session. Thank you for your active participation. I would like to thank ma'am for the demonstrations and with the help of examples and tricks. What she has provided to you is a gem. And with that, I will wrap up this session, and that's the last session for today. But stay connected to NCERT. Namaskar.